Hello there, this is chapter 8.1 and in this lecture we're going to discuss some of the electrophilic addition reactions of alkenes. Let's have a look at the video breakdown. In the first video we will look at a general overview of electrophilic addition reactions to alkenes. In the second video this will then focus in on a specific example known as the hydrohalogenation reaction, which involves the addition of HX, where X is a halogen. In video 3 of 3 we will then consider a second type of electrophilic addition reaction. This is known as the hydration reaction, and these involve the addition of water across an alkene. In general, an addition reaction causes a molecule to be added across a pi system. In this lecture, we'll confine the discussion to the addition across a single pi bond or a double bond. A, in this particular reaction, represents the alkene, and Y represents the molecule that we're adding. Whatever we're adding usually ends up forming a sigma bond, and these two sigma bonds are stronger bonds than the original pi bond. So for example, here we have 1-methyl cyclopentane, and we're adding hydrogen bromide across this to give the molecule seen here. Later, we'll learn that there are nuances that dictate how the molecule adds, but for now, this would give us a cyclic alkyl halide. What is the versatility of this reaction? Let's see. This is a highly versatile type of reaction, and is one that is part of a synthetic chemist's toolkit. Alkenes can be transformed into monosubstituted alkyl halides as shown in the first part of this scheme. This specific electrophilic addition reaction is known as a hydrohalogenation reaction and will be the subject of our next video. Next in the scheme, it is also possible to add water across a double bond. This is the exact opposite of dehydration and is known as a hydration reaction, yielding an alcohol functional group. And lastly, if a diatomic halogen is added to an alkene, it is possible to form the vicinal dihaloalkane. This will be subject of the next lecture. However, for now, let's take a look at the general features of any electrophilic addition reaction. Here we see the map of electrostatic potential for ethene, and this should serve as a reminder that there is a high region of electron density localized in the pi bond between these two sp2 hybridized carbons, and this electron density is distributed throughout both lobes of the pi molecular orbitals. The pi bond breaks as the electrophile approaches. Typically, the sigma bond between the electrophile and the other species, a nucleophile, is also broken. As part of the reaction process, two strong sigma bonds are formed, one to the electrophile and then the other one to the nucleophile. If we think of a halohydric acid like HBr, then the hydrogen atom would behave as the electrophile and the bromine atom then behaves as the nucleophile. Let's now have a look at the reaction from an orbital perspective. The alkene is a nucleophilic pi bond and is attracted to the partial positive charge of the electrophilic hydrogen atom. Now imagine that when the electrophile approaches the alkene, the electrophile, because it's electron poor, may be able to pull the pi bonded alkene electrons out of their bond and into one of its empty orbitals. When this happens, a new sigma bond is formed between one of the carbons of the alkene and the electrophile. Now the alkene's carbon, which was sp2 hybridized, becomes sp3 hybridized. Also, the bond between the hydrogen and the X nucleophile is broken. The electron density was already being pushed towards the X atom as the electrophile approached the alkene. The other alkene carbon, which lost the pi electrons, is still sp2 hybridized, but it now bears a positive charge because its unhybridized 2pz orbital is empty, but it won't stay empty for long. A carbocation is generally a very reactive and unstable intermediate. In an electrophilic addition reaction, a nearby nucleophile, in this case X-, will quickly donate a pair of electrons to form a new sigma bond, and with 4 sigma bonds, the carbon will be changed to an sp3 hybridized center. Note that the nucleophilic X- is able to add from either side of the planar carbocation, which means there is not a stereochemical control of the addition products.
This concludes part A.
In this video, we're going to discuss the regiochemical outcomes of electrophilic addition reactions. In particular, this is with a focus on hydrohalogenation reactions. Here is an example of the mechanism of a hydrohalogenation reaction that involves prop-1-ene with a hydrohalic acid. These are typically HBr, HI, as HCl is too slow to be of any synthetic usefulness. In the first step, the alkene reacts with the hydrogen electrophile and the bond between HX is broken. A carbocation is formed as part of this mechanistic outcome, and the X- anion attacks the carbocation, giving an addition product. This is all well and good when we have a very simple alkene, but how comes the positive charge was on the carbon to the left and not on the carbon where the hydrogen was added? Well, this is owed to regiochemistry. It's time to meet Markovnikov. This famous Russian organic chemist, through his observations in the late 1880s, figured that the major product formed from a hydrohalogenation reaction always has the proton attached to the carbon, which bears more hydrogen atoms. This in turn means that the halide becomes attached to the carbon with more alkyl substituents. This is consistent with the carbocation model, since carbocation stability increases as hydrogens are replaced with carbons. In the reaction of alkenes with hydrogen halides, the reaction will proceed through the most stable carbocation. A way of remembering this is the phrase that the rich get richer. In other words, the hydrogen will add to where there are already more hydrogen atoms on the alkene substrate. Or you may prefer to remember this using this science meme. However, what if you did want to add a proton to the poorer carbon, in inverted commas, i.e. the one with the fewer hydrogens? This reaction occurs via free radical addition, and at the moment we are limiting our discussions to ionic reactions, so there's no need to learn the mechanism for this. This will come up again in chapter 10. For now, you should know that the addition of an organic peroxide or hydrogen peroxide in the presence of a hydrohalic acid, e.g. HBr, will lead to a reversal in the regiochemistry of the reaction. Nothing happens to the stereochemistry of the reaction. There will always be a mixture of syn and anti-products. We call these products, though, anti-Markovnikov addition products.
This concludes part B.
We will be considering a number of different hydration reactions. These are all very similar to the electrophilic addition reactions already seen for the hydrohalogenation reactions, though there are some nuances. For example, there will be a component of oxidation to consider in the next few slides. Hydration reactions result in the addition of water across a pi bond, which in itself then forms a low molecular weight alcohol. In the first step, the alkene behaves as the nucleophile and attacks the incoming electrophilic water molecule. The incoming electrophilic water molecule is the hydronium ion, so there's usually some catalytic acid involved in this mechanism, and that acid is typically sulfuric acid. The reaction occurs via the Markovnikov addition, and hydrogen adds to the side containing more hydrogens. In this case, we have a secondary carbocation, and the water is able to behave as a nucleophile, thus attacking the newly generated carbocation. But in order to get to the alcohol, there is one final step that we'll see on the next slide. In step 3, there is an excess of water, so this is used to deprotonate the intermediate, and alcohol results and the acid catalyst is regenerated. Note that there is an equal amount of syn and antiproduct produced, as the planar carbocation can be attacked from either the top face or the bottom face. But what if you did want some regio control or stereo control from these hydration reactions? Well, we'll look at some useful alternatives, but before we do that, we should note that the acid catalyzed hydration in itself can be problematic, and it is wholly dependent on the nature of the substrate. The issue with acid catalyzed hydration always occurs if there is a possibility for the carbocation that results to rearrange. If there is a more stable carbocation that can be formed, then this will always happen before the nucleophilic attack, as this step is very, very fast. So here we see an alkene substrate where we have the intended site for the OH, and then what actually happened if we use the acid catalyzed hydration reaction. If we wanted to achieve the intended addition, this Markovnikov addition for the OH group without the carbocation rearrangement, then we use a reaction known as Oxymercuration, Demurcuration, and here we see its overall reaction scheme. The first step is known as the Oxymercuration part, and the second step is just the Demurcuration part. Now, this will proceed to give us the Markovnikov product that we intended. Let's look at the mechanism for the first half of this reaction. Oxymercuration demurcuration is a reaction chosen by organic chemists to avoid the carbocation rearrangements that we saw on the previous slide. Now, we use mercuric acetate as the electrophile, and in a concerted step, what happens is that the pi electrons attack the electropositive mercury, and that the lone pair on the mercury forms a bond to the vinylic carbon. All of this happens simultaneously, and there is a loss of an acetate ion. When the acetate ion is lost, we see the mercurinium ion bridge that has been formed in the middle, and this puts most of the positive charge, so it's a partial positive charge, on the more substituted carbon. The water can then attack at this particular center and opens up the mercurinium ion bridge. When it does this, it gives an organomercury intermediate that's still protonated. Water then removes one of those protons, and we see in the last step of this reaction, the demercuration step, that sodium borohydride under alkaline conditions removes the mercury, giving us the alcohol product. Now, it's in this second step that the stereochemistry that was established, i.e. the anti-addition, is scrambled, and so there is no overall stereochemical outcome from this reaction, but there is the Markovnikov addition. What if we want an alcohol product that has anti-Markovnikov regiochemistry, but we still need to avoid any carbocation rearrangements? This is the final hydration reaction of this lecture and is known as Hydroboation oxidation. This particular reaction goes with anti-Markovnikov regiochemistry and is the organic chemist's preferred choice so as to avoid any carbocation rearrangement. The reaction is stereospecific, as there is a syn addition, and this means that the hydroboration process takes place on the same face of the double bond, leading to a cis stereochemistry. Let's have a look at the reaction mechanism of this reaction now. In the first step, borane behaves as the electrophile by accepting the pi electrons into its empty p orbital, and this allows boron to have an electron octet. A very interesting characteristic of this process is that it does not require any activation by a catalyst. However, it is important to understand the structure and properties of the borane molecule. Borane itself exists naturally as a very toxic gas, but it actually exists as a dimer of the general formula B2H6, which is known as diborane. Since the diborane dimer is not only toxic but also ignites in air, there are safer commercially available Lewis acid-base complexes. One such Lewis acid-base complex is when the diborane is reacted with two equivalents of tetrahydrofuran, and the tetrahydrofuran only behaves as a solvent here, so it does nothing to the ability of the borane to behave as an electrophile. Before we continue to look at the mechanism, one should remember that the alkyl groups will act as electron donating groups, and so this should help to explain the regiochemistry that is observed on the next slide. The addition of the borane to the alkene is initiated and proceeds as a concerted reaction because bond breaking and bond formation occur at the same time. The vacant 2p orbital of the boron takes the role of the electrophile and accepts the pi electron from the nucleophilic alkene. The boron adds to the less substituted carbon of the alkene, and this is because of the electron donating nature of the alkyl group attached. Both the boron and the hydrogen add simultaneously on the same face of the double bond. This is what is known as syn addition. With a concerted mechanism, there is no carbocation formation, so there is no need to worry about any possible carbocation rearrangements here. It is important to note that the reaction continues 2 more times until all 3 hydrogens on the borane have reacted with the alkene, and this creates typically a trialkyl borane intermediate, provided that the alkyl chains are not too long, or if you use a cycloalkane, sometimes you will get a dialkyl borane instead. The second step of the hydroboration oxidation process is shown on this slide, and it's worth noting that the addition of H and OH overall is a syn addition, but this is as a racemic mixture. The oxidation mechanism is beyond the remit of this course, but you do need to know the reagents, which in this case are hydrogen peroxide under alkaline conditions, and you will be expected to use this reaction as part of any retrosynthetic or synthetic strategy towards a target molecule. Now let's have a look at the stereochemical aspect of this reaction in a little more detail. Here we see the concerted addition of borane via hydroboration. The first equivalent of hydrogen and the borane are delivered to the same side of the double bond. The subsequent oxidation step did nothing to change the stereochemistry of the original syn addition. So let's have a look at one more example. Here we have a cycloalkene that is not symmetrical. So via hydroboration oxidation, there is a stereospecific syn addition which results in the racemic product seen here.
This concludes part C.